Welcome back to differential equations. In this video, we're going to be looking at phase plane analysis. We saw previously that we can analyze a dynamical system, a system of differential equations, by graphing its phase portrait and trying to classify what's happening there. Let me get my head out of the way and let's dive right into a particular example. This is actually an example we looked at previously. I have that x prime is y minus 1/2 x, and I have that y prime is the sine of x. In order to perform phase plane analysis, the first thing you need to do is learn where the equilibrium points are. Equilibrium points occur when x prime and y prime are both 0. So that gives us a system of equations to solve. Y minus 1/2 x equals 0, and sine x equals 0. Right? It's a nonlinear system, which is kind of annoying, but at least it's not that interconnected. If sine of x is equal to 0, then that means that x itself is going to be 0, or pi, or negative pi, 2 pi, negative 2 pi, etc. And the y values can all be determined from that. Right? Take each of those x values in turn and plug it into the other equation. X equals 0 is going to imply that y is equal to 0. X equals pi is going to imply that y is 1/2 pi, and so on. So now we know where our equilibrium points are. Let me clean this up a little bit so that I can bring the phase portrait onto the screen. And so I listed out the equilibrium points: x equals 0, y equals 0, x equals pi, y equals 1/2 pi. I'm also going to list x equals negative pi, y equals negative 1/2 pi, because that's the last one that fits on the screen. If I bring that phase portrait up and I follow a couple of representative curves, right? So just clicking around, filling in enough detail, looking at places where there's not a lot of detail and trying to click in to see if something else interesting happens, we can look at and spot pretty quickly those equilibrium points. There are 3 equilibrium points. 0, 0 is right here. Pi, 1/2 pi is right here. And negative pi, negative 1/2 pi is right behind my shoulder over here. I can't stand out of the way of everything. I apologize. Let's start with this one, though. We know that this is an equilibrium point, and so our goal is to compare what is happening there to what is happening in the canonical equilibrium points. So kind of imagine drawing a box here and just focusing on that part of the picture. We can see curves that are rotating about and moving faster and faster towards the center. That's the behavior we know about as spirals. So this is a stable spiral, or a spiral sink. If you look at the point over here, negative pi, negative 1/2 pi, you see the same thing happening again. The center point, 0, 0, is a little bit different. At this point, 0, 0, we have these curves. I've gotten really blurry. Let me try to fix that real quick. There we go. Right. Here at 0, 0, we have these curves that are coming towards, but not staying, right? Coming in from one path and leaving on another, coming in from one path and leaving on another. Actually, let me get my head back out of the way and let's draw in a couple more paths around there. And you'll start to really see the pattern that we've talked about before, where everything coming in is coming in following along this nice curve, and then it all spreads out, and then it gets pulled into this curve. Where it comes in over here, it spreads out, and it gets pulled into this curve. Comes in along this curve, it spreads out, it gets pulled into a different curve, one side or the other. That's exactly the behavior that we saw with the saddle point, the semi-stable node in the past. And so we can classify exactly like that. This is a saddle node. This is a stable spiral. And this is a stable spiral. That's really all the more I'm talking about when I'm talking about classifying equilibrium points. I mentioned in the previous video, if we had the mechanisms of linear algebra, we could go on and put some numerical values on this and give a more comprehensive result than just, well, that's what the picture looks like. But that's what the picture looks like is still an important step along the way. It is still something that mathematicians use as part of their process. All right, let's get the phase portrait out of the way a little bit, and let's look at an application. We talked about population dynamics when we talked about phase lines in the first place near the beginning of the course. Now we are going to look at predator-prey models, where instead of having just one population, we're going to have two. But before I get to that, I want to remind you of what a population model looked like in the first place. Rather than just thinking about a population, we saw that giving this number as a percent of the carrying capacity made the analysis make more sense. So we are analyzing a population of something, rabbits in a field, and we know that based on the size of the field, the amount of grass that's growing, that if everything else is perfect, there is some number of rabbits that is the maximum that can be supported. If there are more rabbits than that, then the population is going to start dying off because they're not getting enough food, they're not getting enough space to live. And what we saw is that the rate at which the rabbits grow is equal to some constant of proportionality times the number of rabbits that are there, right? The more rabbits, the more reproducing happens. The fewer rabbits, the less reproducing happens. And then it's multiplied by this 1 minus x factor, which was the distance you are from the carrying capacity. If you are at 1, that is a 100% carrying capacity. If you are at 0, that's a 0% carrying capacity. If you're at 0, there's no rabbits to populate. If you're at 1, you can't add any more rabbits. If you're somewhere in between, the population is going to grow. If you're above 1, you have more than all of the rabbits you can support. The population is going to start falling. Now I want to introduce two related systems. We're not just going to have our rabbits, the population there is going to be x of t. We're also going to have foxes, a predator who wants to eat the rabbits. And now here, things get obviously more complicated. We know that x prime and y prime are both going to be functions of t, but they're really going to be functions of the numbers, right? The more rabbits there are, the faster they're going to grow. So you're going to have some constant times x. That's going to be part of the equation. I'm going to have more equation to write later. I know that the more foxes there are, that's actually a problem. I mean, yes, the foxes have to reproduce, but foxes are always worried. The more foxes there are, the less there is food to go around. So the number of foxes is actually going to decrease the rate at which the population grows. But I know that the foxes are going to feed. Each rabbit is going to feed a fox or could feed a fox. The rate at which foxes eat rabbits is given here. And the more rabbits there are, the bigger the population of foxes can grow. Of course, the more foxes there are, the slower the population of rabbits will grow. All right, that's going to function like my 1 minus x term. But instead of just being 1 minus x, it is some function of x and y. The more foxes there are, the lower the carrying capacity because the rabbits are going to get to the point where they're being hunted down by foxes. So this gives us a new dynamical system. So again, we have a rate at which rabbits are breeding. That's R. We have a rate at which foxes are starving. That's S. We have a rate at which the rabbits are being hunted. That's H, and it depends on both the number of rabbits and the number of foxes. We have a rate at which the foxes are being fed. That's F. It might take more than one fox to hunt a rabbit. It might take more than one rabbit to feed a fox. So F and H might not be the same value, but they should be in some way related to each other. This is a nonlinear system. So we're going to analyze it using a phase plane. We're not going to try anything fancier than that for right now. I just have to pick some values. So if I pick, say, r equals 0.3 and h equals 0.1, if I pick that s is 0.2 and f is 0.05, that's going to give me one model. Again, I could pick different numbers and get a different model if I wanted to. One of the things that is interesting whenever we are looking at a dynamical system is looking for equilibrium points. This is going to be a nonlinear system. 0.3x minus 0.1xy is equal to 0, negative 0.2y plus 0.05xy is equal to 0. And a couple of ways that you can approach this. I'm not sure if I could say that any one or another is the best bet. But one of the things that I see pretty quickly is that if I take the first equation and I multiply by 10, I take the second equation and I multiply by negative 20. I can then subtract these two equations and get that 3x minus 4y equals 0, which is the same thing as saying that y is equal to 3/4 x. So my equilibrium points are going to be along this line. That's not the end all be all. That's not going to be that every equilibrium point is on this, or that every point on this line is an equilibrium point, but it gives us something to play around with, something to start off with. And honestly, that's going to be good enough for us right now. All right, let me, whoops. All right, here we go. There is our phase plane. Although I could probably zoom in a little bit because having a negative value for x or y doesn't really make any sense. So let's go ahead and change around my limits. So I have here now from 0 to 6 in the x direction and in the y direction. And if I click in and draw a couple of representative curves, I see some interesting things happening here. Right? I see that at 0, 0, I have what is looking like a saddle point to me. Um, at 0, 0, things suddenly shift from the population of foxes is dropping to the population of rabbits is growing. And that makes quite a bit of sense. If the population of rabbits is 0, then the foxes have no food and the population of foxes is going to plummet. If the population of if the population of foxes is 0, then the rabbits have no predators and the population of rabbits is going to skyrocket. If you're somewhere in between, then you're somewhere in between. And specifically what we see here, if I look over my shoulder on this, is we see that there is a center right here at x equals 4, y equals 3, which is not the only point on that line, but definitely a point on that line. And at that point and at things around that point, we are seeing these cyclic patterns. The population of rabbits is going to grow, which is going to cause the population of foxes to grow, which is going to cause the rabbits to be hunted and the population of rabbits to shrink. And then when there's fewer rabbits, the population of foxes is going to shrink. Now there's fewer foxes and the rabbits are going to excel. And you're just going to get this cyclic pattern. And if you think about it, that probably makes sense in a seasonal sense. In the winter, the rabbits are in hiding. It's difficult for the foxes to find them, and the new generation of rabbits is bred. In the spring, the rabbits come out. There are a lot of rabbits, and the foxes are happy to find them. The foxes hunt out the rabbits. The population of rabbits drops. As summer continues, there's fewer rabbits, the foxes are finding it more difficult to survive. The population of foxes is going down. And then in the fall, now that there's fewer foxes, the rabbits are a little bit safer. They can breed again, and the cycle continues. So there's the idea. There is one particular application of how this is going to work. As we wrap up, I want to, excuse me, I want to go back to the one that we looked at previously. So I had you look previously at x prime equals cosine of y and y prime equals 2x minus y. Now I want you to go back to that graph and find and classify some equilibrium points. Right, so take a couple of minutes, see what you can do with that, and I'll see you in the next video.